All right, little red lights blinking. Everybody see G3B?
Yes.
Okay. Um, we're going to talk a little bit about the MUF and the LUF and long and short path, um, and how you can determine propagation conditions, and a little bit about ionospheric refraction, since that's how you get long distance communications. So, as it mentioned in the video, the MUF is called the maximum usable frequency that will still refract a radio wave back to the Earth. Now, if you had a frequency higher than the MUF, it'll still have refraction and be bent, but not bent enough to make it back to the Earth. Uh, and like they said, the LUF is the lowest usable frequency, which is affected more by absorption and things like that. So you normally can operate between those two as long as the MUF is greater than the LUF. And like they pointed out, and it is a test question of what
Mhm.
happens if the LUF becomes greater than the MUF. The bottom line is you cannot
Okay.
communicate. There is going to be no refraction. Uh, talk about the short path and the long path when you're uh, looking at a uh, communications path between point A and point B. The shortest distance uh, over the surface or through the ionosphere is called the short path. 180 degrees from that, which means you go in the opposite direction, you go a much longer way around to get to that same point, they call the long path. It's possible due to propagation conditions that you get a stronger signal via the long path than you do the short path. Doesn't happen often, but it's potential. It's also possible to have conditions good enough that both the short path and the long path work, and you receive the short path signal, and then in a delay, you receive the long path signal. So you hear an echo. Okay, so the MUF is the maximum usable frequency. There's that formula they used, and the cosine of theta is the incident angle. In other words, um, the elevation angle of your uh, wave. if it's if it's perpendicular to the Earth, then the cosine of 90 is going to be 1. So it means the MUF is going to be equal to the critical frequency. As that angle decreases, then you're going to have a value of cosine less than 1, somewhere between 0 and 1. So it means that the MUF is going to be um, greater than the critical frequency. And I think they said in the video like 3 to 5 times. The LUF is the bottom end, okay? And like I said, it's really affected by how active the D region is, because that's absorbing the lower frequencies. So the more absorption you're having, the more it's going to raise the LUF up to the point where the LUF starts to equal the MUF, and then you're in trouble. Uh, so the reason path distances listed because the longer the path through the D layer, the more absorption. So you have less and less signal. So that's why it depends on the distance and the location. Also, the time of day, because uh, during the day you're going to have more absorption than you are at night, and the seasons also, summer and winter, will have an effect on it. And obviously, the amount of solar radiation and ionic disturbances are all affecting, you know, how active the D layer is. So the more active the D layer is, uh, the more it's going to affect the LUF. And actually, the D layer, I don't know why I said that. D layer didn't have to do with the MUF. Um, hmm, guess I was having a brain fart.
That's okay. I got a quick question for you,
Okay.
Rob. You said on the path distance and location, you said during the day, the distance is greater than at night. Is that what you said?
No, I said absorption or refraction in this case is going to be greater.
Okay. Okay. That's right. Okay. Thank you.
The Is everybody familiar with what refraction is?
I've looked those words up, but I forget them, to be honest.
Okay,
As,
do you
as
worry?
distinct from reflection, right? Refraction and reflection.
They're different.
Yeah. How?
Do you wear glasses?
Yes.
Okay, and you went to a ophthalmologist or optometrist and got a refraction, right? For a eyeglass prescription. That's what they call it, and they charge you like $100. What they're
So,
doing is measuring um, how much index of refraction they need to put in your lenses. So
refraction.
remember, light is also an electromagnetic wave, and it works the same way. So if you have an electromagnetic wave that's hitting an interface between two materials that have different index of refraction, it causes that wave to curve, just like light going through a piece of glass at an angle, because glass has a different index of refraction than air, will cause the light to bend. We call it refraction.
This is why when you put a stem of a flower in a vase,
Right,
yes.
exactly.
Okay.
Well, the ionosphere works the same way. The different layers have different indices of refraction because of the density. Uh, so when your when your transmitted wave is at an angle to one of these layers of the ionosphere, part of the wave is in a higher index of refraction than another part of the wave, so it causes it to bend just like light wave through water or glass. And if it's bent enough, it will bend back down and reach the earth and possibly be reflected off of the earth. That's not refraction, that's reflection.
So refraction is the bend and reflection is the bounce.
Right.
Good one.
And you can have multiple bends and bounces.
Okay.
In fact, if you were to make contact from here to somebody in China or Australia, because that's probably further, you're going to have a number of bounces because even off of the F2 layer, you maybe get a couple thousand miles. So it's got to hit the earth or the ocean, preferably the ocean, because that's a much better reflector, and back up to the ionosphere and back down. So you may have that happen a number of times to actually get to that point, 10, 12,000 miles away. And like I said, all these things are affected by the time of day. Uh, Daytime is better for refraction of the higher frequencies. It's worse for lower frequencies because they tend to get absorbed in the D layer. So any frequency above the MUF, okay, is a frequency that's going to be bent, but not bent enough to make it back to Earth. And the higher the frequency, the less bending, and it'll just go out into space. If you're operating between the MUF and the LUF, okay, then chances are pretty good that your wave is going to get bent back to Earth, depending on the ionization of the ionosphere and how high your wave, well, partly the angle and how high your wave goes through that and gets bent, the farther it's going to go. So if you think of it getting to the very top of the ionosphere, the top of the F2 layer, and being refracted, that's going to give you the longest hop because it's the highest layer. Whereas if you're getting some of the lower frequencies and they're being refracted down at the bottom of the F1 layer or in the E layer, it's going to give you a much shorter hop. And the main thing here is if the LUF ever exceeds the MUF, you'll get no HF skywave communications. You'll still have line of sight and you'll still have ground wave, but you won't have skywave. So the closer you get to the MUF, the least amount of attenuation you're going to have in your signal. So it's optimum to operate as close to the maximum frequency that you can to get the least amount of attenuation and the longest hop. Particularly
Attenuation?
if you, excuse
What do
me?
you mean by attenuation?
Signal loss.
Okay. Like strength?
Like what?
Strength? The strength of the signal?
It affects the strength, yes.
Okay.
Your signal loses energy
Yep.
because of absorption and
Mm-hmm.
some reflection because there's also particles that can scatter your signal.
Okay, so I just want to clarify. I'm looking to be in between the MUF and the LUF.
Right.
And reading this, it says just below the MUF, which means it's not quite centered. Is that the issue?
Yes.
Okay.
The closer to the MUF or the higher the frequency below the
Yeah.
MUF,
Right.
it's going to be your best propagation.
But it has the lowest attenuation.
Right.
Which is a good
Which
thing.
means
And
means it's not very straight. It loses power.
you'll have more power, or you'll
Oh,
lose
more
less
power.
power. You
Okay,
won't gain
loses.
power, but
Okay.
you won't lose as much power.
Okay, now I understand. I was just the words weren't okay.
And you get up to the highest altitude before it refracts back, so it'll go
Okay.
farther.
So when
So
you say the lowest attenuation, you're not saying the lowest power, you're just saying the lowest interference in the power.
Yes.
correct, right?
Okay.
Because your signal going through the ionosphere, just like going through, low frequencies are absorbed more in the D layer, but all frequencies are absorbed a little bit going through the ionosphere. So the higher frequencies are absorbed less than the lower frequencies. That's why having a frequency closer to the MUF has less attenuation or
Mhm.
less absorption.
In
That
other
makes
words, the best bounce, the best strength is if you go all the way up as close as you can to the maximum usable frequency.
correct.
That's the
However,
best.
right,
But it'll work below that down to the lowest usable frequency.
right. So even though operating at the MUF would give you your best propagation, that may not be the frequency you want to operate on.
For some other reason, like you don't have an antenna.
Well, maybe the station you want to contact is on 40 meters. Not a good choice for the daytime, but um, there's various reasons why you might want to operate at some other frequency than the MUF or right next to it. Uh, one of the things you can use to determine propagation, there's a lot of online, uh, sources that will show you propagation maps, and they're updated fairly frequently. And it's kind of a color coded uh, thing which shows where the areas of best propagation are. And this is not a linear phenomenon. It's not like uh, the ionosphere layers are uniform. They're not, and they vary during the day. I mean, just think of them like clouds. You know, some of them are denser. Some spots are denser than others, and
Mm-hmm.
So these sources that generate these propagation maps,
uh-huh.
who are they and how do they make money?
I don't know that they're in it to make money. Uh, uh, I don't see how they would make money.
So are they
Some of them,
public
yes,
sources?
public. I think some of them might be government. I think I have a chart showing one, if I remember. We'll see. The other thing is, you just listen for beacons. There's
Mm.
uh, there's a lot of beacons around the Earth that are at fixed Earth locations, which send out signals on particular frequencies. Remember, we talked about those early, where you can have one beacon per band.
Mm-hmm. I have a
Uh,
question though.
okay.
If I'm listening to a beacon and I hear the signal from the beacon, I don't want to necessarily be on that frequency because then I'm interfering with the beacon, correct?
Well, right, but it means that band is
But
pretty.
I'm
It's the band is pretty good if you
yeah,
can
so
hear
I
the
can
beacon.
maneuver within that band and avoid the beacon and still use it.
Yes, in fact, you're supposed to avoid the beacon frequency,
Right. Right.
but they're just there. If you can hear them,
Then you're in
uh,
a good place.
you know, and especially more than one, then it
Mm-hmm.
tells you how good the bands are at that particular time, and it may
Right.
change in 5 minutes.
Right.
That was one of the things where we talked about interference, where you're communicating with somebody, and all of a sudden you hear some other person talking on the same frequency because the propagation changed. Let's see. And the short path and long path are pretty much explanatory. The long path is 180 degrees out from the short path, and it's the longest way to get from point A to point B, whereas the short path is the shortest way to get from point A to point B. And if you have propagation via both, which is uncommon, but it can happen, you'll hear two signals. One maybe not as strong, but it's possible the long path could be stronger.
So again, to clarify the both signal part, if you're using the short signal, it is possible it can take the long path and come back in an echo. But you're not using short and long at the same time. It's just that
Well, you don't have a
you're
choice.
projecting. Okay, so it's going to choose its path.
Well, right. I mean, you're
Okay.
sending a signal out. Well, unless you have a very directional antenna, it may be sending it in multiple directions.
Okay.
Even with a directional antenna, like a multi-element Yagi, you're going to have a rear lobe. So you're going to radiate in 180 degrees some amount of energy, even though most of it is going to be in the forward direction. Some of it's going to be in reverse. So that's going to be going over the long path.
Okay.
So it's possible, if the long path is good enough, for that to make it all the way around.
Cycle
And
around,
that
yeah.
person that's listening to you is going to hear that echo. Likewise, the same thing can happen to you. You know, they're sending it and you're getting it both ways. Like I said, it's a rare thing, but they thought, it ought to be a question. So that's why it's there.
I have experienced that on cellular phones.
Okay.
So I understand what you're,
Echo
yeah, the
or
echo,
short, long path?
the echo from the long path, I'm assuming.
Are there, well, this is one cause of echo, but I'm wondering if it's the only cause of echo.
Well, I think it's the only one we talk about with HF.
Right. So is cellular HF?
No. Cellular is VHF, UHF. You shouldn't be hearing an echo because you shouldn't be in connection with more than one cell tower at a time. And they do switch because they monitor signal strength from various cell towers, and they will switch you automatically, you don't know it, between cell towers depending on signal strength. But you shouldn't.
More than once I've actually been on the phone and I can hear myself. I can say it and then I can hear myself again. That's
Really?
I've
happened.
had that experience too. Yes.
Yep. More
It's
than once.
it's pretty much
It's
impossible to carry on a conversation when that's
Yeah,
happening.
you have to try. Yeah, you have to try to totally ignore the fact that you're going to hear yourself again.
Which you can't. I mean, I can't.
I
Maybe you
know it's
can.
hard. It's hard.
Yeah, you just have to
I
have
usually
a
say,
thought,
I
you know.
hear an echo, I'll call you back. And that's the
Yep.
end of that.
I
Yeah.
don't think that's short path, long path. I think that's something else with the connection. Okay. Any other questions on that?
Nope.
So this is all about, just to clarify, not a question.
Okay.
The way I imagine this is if I have an antenna or if I had a thing and I was a straw, say, and I'm blowing water into a hole in the straw, the water might very well go out either end. The water would go out either end of the straw. And one end is the short path, and the other end is the long path. And just the signal is squirting out both ends of the antenna, maybe not in a straight line, I understand, and that's what the short path and long path are. That's how I picture it. A straw, hole somewhere in between the two ends,
Well, I guess
blow into it, squirt water out. You
I
like
guess
that
that's one
picture?
way to look at it.
It's almost as good as the vase.
Okay.
So fair enough, not too off. Doesn't matter what the
Yep.
frequency is, this could happen, right?
Yeah, well, if that helps you, that's fine.
All righty.
But main thing is the long path will always be 180 degrees from the short path.
Like a straw. Like a straw. You didn't get my picture, did you? It's okay.
Okay. Let's see.
I follow.
Thank you, Annette.
Um, atmospheric noise is another issue, particularly on the lower frequencies. 40 meters and 80 meters in particular, in the summertime, you not only have a lot of normal atmospheric noise and static, uh, if you have thunderstorms, which tend to be more in the summertime, that will increase that noise, and you'll hear those lightning discharges and things. So it becomes very hard to try to do the low frequencies, especially in the daytime in the summer. Here's a um, thing I found that I think I sent you a link to this. It's called Open Ham Clock, and
Uh-huh.
it's an application that has a lot of useful information. One of the things it shows is kind of like spotting of uh, who is reporting hearing signals. Uh, People can connect to some of these reporting type sites and list stations that they hear, and they show up on maps like this. So you can see, knowing where you are, which I guess in this case it was over here where the DE is, which is a kind of a CW shorthand for like this is or here. Not sure the exact definition, but like when you're making a contact on CW, you'll usually do uh, the person's call sign you're trying to contact, followed by DE, followed by your call sign, which is basically saying XYZ, I'm ABC type of thing.
Mhm.
Uh, but it has a lot of useful information. It's probably worth looking at. It's a pretty popular thing a lot of people use, um, especially for what they call spotting. So you can see where activity is and who's on the air listening and talking.
Oh,
It even, like down here, has got a POTUS station. Um, there's a couple others like PSK Reporter that shows you a map like this for PSK activity. There's also one that does Whisper. Um, that's a lot like beacons. There's a lot of things that generate Whisper protocol. Pico balloons use Whisper protocol, where you launch a little 3-foot balloon that goes up with a tracker and goes around the earth and transmits over Whisper about once every 3 minutes, and you can track it all the way around the earth. I had one that made 5 revolutions before it went down in the East China Sea.
that's pretty impressive. I keep thinking, did the turtle eat it afterward when it fall in the ocean?
I don't know, but actually it ran into a typhoon called Kraken, and the last thing it transmitted was descending altitude rapidly.
That's pretty cool, though.
Okay, so what is a characteristic of skywave signals arriving at your location by both short path and long path? We
Gosh,
talked this
I
one
can't
to
hardly remember this.
Delta.
Gee, the echo again. Yeah, the echo.
all right. What factors affect the MUF?
Delta.
All of Delta.
Delta.
All of
Yep, pretty much everything. Which frequency will have the least attenuation for long distance skip propagation?
Alpha.
them.
All you have to do is talk with us for 5 or 10 minutes and we'll
There you
remember.
go.
Which of the following is a way to determine current propagation of a desired band from your station?
The beacon, so alpha.
Alpha.
Yep.
Hmm. Hmm.
That's those beacons, right?
Is that, yeah, is that the beacon thing? Okay.
How does the ionosphere affect radio waves with frequencies below the MUF and above the LUF?
Uh,
Alpha.
alpha.
Alpha, yeah.
Alpha. What usually happens to radio waves with frequencies below the LUF?
Alpha.
Charlie.
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 Oh, yeah. I was thinking they don't go anywhere. Which
Well,
Yeah, I think we, yeah,
they get absorbed. That's why they don't go anywhere.
right. So I missed the. I guess yeah. So they're not going back to the Earth. They just don't. They just disappear.
Right. All the
Yeah.
energy gets absorbed in the D layer.
Got it.
What does LUF stand for?
Alpha.
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 Okay. What does MUF stand for?
Maximum.
Bravo.
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 I want to say beta. Bravo.
What is the approximate maximum distance along the Earth's surface that is normally covered in one hop using the F2 region?
Oh,
Gonna guess.
I don't know
Alpha.
if I covered that.
I don't
I'm gonna-
remember that.
no, of course not, Bob. You never said.
Yeah, right. I'm gonna
I guess alpha.
guess Alpha.
I
but
might have
that's just a
implied.
guess. It's going to turn out to be 12,000 miles.
I know, right?
Charlie, yeah.
Well, I'll give you a hint. It's not Alpha
Okay.
and it's not Delta.
Oh,
All right.
somewhere in between.
Charlie.
Bravo.
We have covered the bases.
Oh, of course. That's Charlie.
500.
2,500. So it
2,500.
goes. The approximate distance along the Earth's surface is normally covered in one hop on the F2, which is the highest. That's why it's
Right.
so far.
Using the highest frequency at at the best time,
That's why it can travel that far.
you can get up to 2,500 miles in one hop.
So I'm just going to remember F2 and 25. Got it.
So that means if I'm doing 2,500 miles, a second hop would get me 5,000, a third hop would get me 7,500, and a fourth hop would get me 10,000. So it would take 4 hops minimum to get to Australia.
And so I had something where my mentors were explaining to me, I was trying to reach a friend on the west coast of Florida, and we were using 20 meters and they were saying that this is just sailing over his head.
Right,
And this is one hop was, of course, almost California. So
right.
if those were the conditions,
Which
that,
means nobody but in that 2,500 miles, or almost nobody, would hear you.
right, exactly. So yeah, this is great. Like it. Thank you.
Which is why for short distances, besides doing e-scatter, a lot of people use what's called NVIS, NVIS, and I think we talk about in the next section,
All right, cool.
which is essentially directing your emission vertically so that you're actually reflecting off of the ionosphere and you're coming back down in very short distances, so you can get like 100 miles or 200 miles away,
Interesting.
which would allow you to talk to somebody in Tampa. But if you were on 20 meters during the day, uh, unless you had and well, and 20 meters, even if you had your antenna pointed up, it's going to go through. So
Yeah.
it's
Yeah.
about the only way to do it.
Yeah.
What is the approximate maximum distance along the Earth's surface that is normally covered in one hop using the E region?
We didn't talk about that either.
Yeah, I must have lost a slide or two.
Yeah. But E is less than F, so it's got to be less of a hop, right? So
Correct.
180 is too short, so it's got to be big.
Got it. So Bravo.
I
Yeah.
guess Bravo. We're guessing.
Good
Yeah.
All
guess.
right.
Good guess.
Yay! Good.
No.
Yeah.
So even a E hop is going to be too large for Tampa.
Right.
Mhm.
What happens to HF propagation when the LUF exceeds the MUF?
Forget about it.
Can't make any connection. Yeah.
You can
So,
do,
Alpha.
yeah.
Alpha.
oh, yeah.
Which of the following is typical of the lower HF frequencies during the summer?
Got a lot of noise. Yeah. So delta.
Or alpha. No, wait. No. This is the atmospheric interference, isn't it?
Right.
So that would be
So delta.
delta.
Okay. I'll have to go see what happened to a couple slides.
This is where you say, aren't we doing well?
Well,
Yeah.
you are. You're doing
I
amazing.
think we are actually.
Not too bad. Yeah. You want to cut off your recording?